Hello students. So today we will be discussing about the energies of the orbitals. Okay. So what are going to be the energies and what is going to be the order of the energy of different orbitals in an atom for the electrons. Okay. So here as you can see that energy of electron is determined solely on principal quantum number. Correct. So if it does so, then energy of the orbitals are given as in this order, where one is called the ground state energy or lowest energy level, then 2s and 2p, since both these two orbitals are in the same quantum number 2, n equals to 2, so both have the same energy, both should have the same energy. Then 3s, 3p and 3d under principal quantum number n equals to 3 have to show similar energy. So 3s, 3p, 3d are of similar energy. Then 4s, 4p, 4s, 4p equals to, this would be equals to 4s equals to 4p equals to 4p equals to 4f. All these 4s, 4p, 4d and 4f orbitals have the same energy. So this is going to be the order of energy of different orbitals under particular different values of principal quantum number n. Correct? Because energy of electron solely depends on the principal quantum number n. So under the particular value of n, all the orbitals will have the same energy. Okay. Now another point is that the closeness of the orbitals to the nucleus is given by s orbital, then p orbital, then d orbital, then f orbital. S orbital is the closest to the nucleus, then p orbital, then d orbital, and ultimately f orbital is largest distance apart from the nucleus. Now this for this reason, the electron in the 1s orbital, since 1s is the ground state and since s orbital is the most closest orbital to the nucleus, so 1s orbital electron will be tightly bound with the nucleus, since s orbital since for 1s orbital n equals to 1 and s orbital is closely is very much close to the nucleus, so 1s orbital electron is tightly bound with the nucleus, and that's why the energy of the electron in the 1s orbital is the lowest, and that's why 1s orbital is called the ground state. Okay. Or ground energy state for electron. 1s orbital is the ground energy state, and consequently the 2s and 2p and the rest orbitals are called the excited states of electrons, because their energies are higher than 1s. 1s is the orbital with lowest energy, since 1s orbital is the most close to the nucleus. So electron in the 1s orbital will have the lowest energy, and 1s orbital is called the ground state. Clear? Similarly 2s and for this reason 2s and 2p, since they are present in the n equals to 2, so they are called the excited state. Now in case of multi-electron system, the electrons which are present in the outer orbit will experience a repulsion force with the electrons in the inner atom, that is inner shell. Between the inner shell electrons and between the outer electrons there will be repulsion in case of multi-electron system. That means in case of the atoms which contains more number of electrons, more than one number of electrons, in that case there will be inter-electron repulsion between the electrons, and for this reason the outer electron will not experience the total positive charge of the nucleus. The outer electron will not experience the total positive charge of the nucleus, because the inner electrons will act as a screen or shield, and it will screen the outer electrons to experience the total nuclear charge of the nucleus. And for this reason the outer electron will experience a less attractive force towards the nucleus because of the presence of these inner electrons. Clear? So because of the presence of these inner electrons, the outer electrons will experience a less attractive force towards the nucleus, and this less attractive nuclear force or this less nuclear charge that the outer electron experiences in case of multi-electron system is called the effective nuclear charge, or it is called the Z effective. So Z effective is only applicable in case of multi-electron atom. Okay, because in case of single electron atom, the outer electron, only the outer electron is present, and it will experience the entire positive charge of the nucleus. It will experience the entire attractive pull towards the nucleus. So there is no problem in case of single electron system like hydrogen. But in case of multi-electron system, due to the presence of the inner shell electrons, the outer electrons will not experience the total nuclear charge or the total attractive force towards the nucleus. Hence, it will experience a less attractive force towards the nucleus, and due to the screening of these inner electrons, and this less attractive force that the outer electrons experience towards the nucleus is called the Z effective. That means effective nuclear charge. Okay. Now, so here we will discuss about the shape of the orbitals. Okay. What are going to be the shapes of different orbitals S, P, and D and F, and what are their probable orientations in space. So first of all, I told you that psi square gives us, psi is a mathematical function that describes the coordinates of the electron's position in atom, and psi square gives us the probability density of electron in an atom at a different radius of the atom. That means at different point of the atom, at a different radius of the atom, psi square will give us the probability of finding the electron in that atom. So if I join the dots, if I join the points where the probability could be found, and then we could get probably a shape of or you can say a region where the electrons could be found, or where the probability of finding electron is maximum. So this geometrical shape that we obtain by joining the points of psi square in space is called the shape of the orbitals. So if I talk about the shape of S orbital is spherically symmetrical. Similarly, since 1s orbital is smallest size at smallest orbital, so 1s orbital is smallest in spherical, smallest sphere. 2s orbital is little larger, and 3s orbital is much more larger. Now, in case of these orbital, you see, there you will find in these orbitals 2s and 3s, you will find one region where the probability of finding electron is almost nil. Okay, that region where the probability of finding electron is nil or is zero is called the node. Okay, is called the node. Now, in case of 2s orbital, you see that there is a node present, because the red area, the red marked area is the area where you could get the electrons, or you can say where the probability of finding electrons is maximum, and this white region is the region where the probability of finding electrons is almost zero. So here there is a region where the probability of finding electrons is zero. So here there is a node. Okay, there is a node, and this node is spherical node. Okay, so this node is called the spherical node of 2s orbital. Similarly, in case of 3s orbital, since the orbital is bigger in size, and these electrons could be found in these positions. Okay, and there is also two spherical nodes are there present in this 3s orbital. So in case of 1s orbital, there is no node. In case of 2s orbital, there is only one node. In case of 3s orbital, there are two nodes. So you can say that number of nodes in an orbital is equal to the n minus 1. Okay, where n is the principal quantum number. So for 2s, n equals to 2. So number of nodes will be 2 minus 1 equals to 1. For 3s, n equals to 3. So number of nodes will be 3 minus 1 equals to 2. And these two nodes are called radial node or spherical node. Okay. So what is the formula of spherical node? N minus 1. There is another type of node is there, that is called angular node, and that is equals to n minus L minus 1. Clear? N minus L minus 1 angular node, n minus 1 spherical node. Clear? That we will discuss later. Now we will talk about the shapes of p orbital. Since for p orbital the ml values are -1, 0 and +1, so there are three p orbitals are possible, which are px, py and pz. And for px ml value is -1, for py it is 0, for pz it is +1. Okay, so in p orbital is dumbbell set, and you can see the two lobes of the dumbbell. These are the two lobes of the dumbbell which are oriented along x-axis. So it is px orbital. When the two lobes of the dumbbell are oriented along z-axis, it is pz, and when they are oriented along y-axis, it is py. Clear? Now, in case of d orbital, we know that there are 5 d orbitals possible, since L value for d orbital is 2, so ml values will be -2, -1, 0, +1, +2. So there are 5 d orbitals possible, which are dxy, dxz, dyz, dx square minus y square, and dz square. What are the shapes? Here you can see dxy, dxz, and dyz have the similar type of shape, where the you can think of, or you can imagine that two dumbbells are fused together, and they are fused in such a way, the two dumbbells are fused in such a way that the lobes are present. In case of dxy orbital, the lobes are present in between x and y axis. The lobes are present in between x and y axis. Okay, in between x and y axis, the lobes are present. In between x and y. This is x, this is y. So in between x and y, the lobes are present. In between x and y, the lobes are present. Clear? Similarly, in case of dyz, in between y and z, the lobes are present. In case of dxz, in between x and z axis, the lobes are present. So these are the shapes of the d orbital. Now in case of dx square minus y square orbital, the same kind of shape you obtain, but here the lobes are oriented along the axis, along the x and y axis. Here you see the lobes are oriented along the y axis and along the x axis, not in between the axis. Clear? In case of dxy, dyz, dzx, the lobes are oriented in between the axis. In case of dx square minus y square and dz square, the lobes are oriented along the axis. Clear? Now in case of dz square, you see the lobes are oriented along the z axis, and there is a concentric ring that is present in the xy plane. Okay, this ring is present in the xy plane, and the plane of this ring is xy, and the orientation of this orbital is along z axis. Both are perpendicular to each other, and this is the shape of pz orbital. Sorry, shape of dz square orbital. So questions can come. What are the shapes? Write and draw the shapes of s, p, and d orbitals. So here you have to draw all the shapes. Okay. Now, as we have discussed, the orbitals under same n value will have the similar energy, correct? Now, since we have now realized that the different orbitals, electrons in different orbitals are differently attracted by the nucleus, and according to that concept, different orbital electrons will have different energy. So that concept that under a particular n value, all the orbitals will have the same concept, will have the same energy, that is not true. Okay, different orbitals, electrons in different orbitals will have different energy, because different orbitals are differently attracted by the nucleus due to the presence of other electrons that are present as inner core electrons. Okay, so due to the presence of those electrons, different orbitals, electrons of different orbitals will be attracted differently towards the nucleus, and hence we can say that orbitals with higher n plus L value will have higher energy. Orbitals with higher n plus L value will have higher energy. If two orbitals have the same n plus L value, then orbitals with higher n value has higher energy. So according to these two concepts, that the energies of the orbitals can be distributed or can be given by, the energy order can be given by this: 1s less than 2s, then 2p, then 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5p, 6p, 7s. All these energy order has been made by keeping thing in mind that orbitals with higher n plus L value will have higher energy. So I am giving you an example, like in case of 2p orbital and 3s orbital. Since in case of 2p orbital n equals to 2 and L equals to 1, so 2 plus 1 n plus L na, so 2 plus 1 equals to 3. Here in case of 3s orbital, n equals to 3, L equals to 0. S orbital, L equals to 0. So 3 plus 0, 3. So both these two orbitals have the same energy, have the same value of n plus L. But since n value is higher in case of 3s, in case of 3s the n value is higher, na? N equals to 3 here. So 3s will have a higher energy than 2p. Otherwise, all the orbitals will have this energy order according to the rule n plus L. So higher orbitals with higher n plus L value will have the higher energy. So I am giving you an example like 4p and 5s. For 4p, n equals to 4, L equals to 1. So total n plus L value will be 5. Here also, if 5 for 5s, n plus L equals to 5. But since for 5s, n equals to 5, higher n value, so 5s will have a higher energy. Okay. If we compare 1s and 2s, for 1s, n equals to 1, L equals to 0. So total n plus L equals to 1. For 2s, n equals to 2 and L equals to 0. So total n plus L will be 2. So 2s, for 2s, n plus L equals to 2. For 1s, n plus L equals to 1. So 2s will have the higher energy than 1s. Similarly, for 2p and 2s, n plus L for 2s equals to 2. N plus L for 2p equals to 3. Because n value is 2 and L value is 1 for 2p. So 2 plus 1 equals to 3. So since 3 is greater than 2, so 2p orbital has higher energy than 2s. So all these energy order can be understood by pictorially by this diagram. Here you can see as we go in this way, that first it will come as 1s, then you have to go in this way, then 2s, then you have to go in this way, then 2p, then 3s, then again go in this way, 3p, 4s, then again go in this way, 3d, 4p, 5s, then 4d, 5p, 6s, then 4f, 5p, 6p, 7s, and then 5f, 6d, 7p, 8s. So this is going to be the order of the energy of the orbitals. Clear? Now we are going to discuss about the Pauli's exclusion principle. Pauli's exclusion principle is saying no two electrons in an atom will have the same set of 4 quantum numbers. That means you will never find 2 electrons in an atom who have the same values of all the quantum numbers. Okay, let's discuss or elaborate this point. Suppose I am talking about the 2 electrons present in the px orbital of p. P cell, in the p subcell, in the px orbital, there are 2 electrons. I told you for each room, for each orbital, there is a capability of holding 2 electrons. Correct? So suppose this is px orbital, and in this px orbital there are 2 electrons. Okay? So for this first electron, what is the value of n? N value is n equals to 2. Since it is present in 2px orbital, so n equals to 2. Since it is p orbital, so L equals to 1, and mx value will be minus 1. Clear? Now for the second electron, same, n equals to 2. Since it is present in 2px orbital, so n equals to 2, L equals to 1 for the second electron, and for the second electron, mx value will be equals to minus 1. Clear? So for these 2 electrons, n value equals to 2, L value equals to 1, and mx value equals to minus 1. But they have different ms values. The ms value for the first electron is plus half, since it is in the clockwise direction, it is spinning in the clockwise direction, and the ms value is minus half for the second electron. So you will never find 2 electrons in an atom for whom all the quantum numbers are same. Maximum 3 quantum numbers could be same for 2 electrons, but at least one quantum number must be different. And this is the principle, Pauli's exclusion principle, that no 2 electrons in an atom will have the same set of 4 quantum numbers. Okay. Okay. Now we are going to discuss the Hund's rule of maximum spin multiplicity. Now, we have already discussed the Pauli's exclusion principle and the energy of different orbitals for an atom. Now, Hund's rule, according to Hund's rule, that electrons are going to be filled up in the orbitals like px, py, pz, like in all the 5d orbitals. Okay, so electrons are going to be filled up in those orbitals like p orbital. That means p orbital means in the 3 orbitals of p. In the d orbital means in the 5d orbitals of d. F orbital means in the 7 f orbitals of f. So electrons are going to be filled up in such a way that firstly all the electrons will be filled up as a single electron for each orbital. Single electrons will be filled up. When all the orbitals will be filled up with single electrons, then if the electrons are present, then electrons will be paired up. Okay, otherwise not. So the principle is saying that pairing of electrons in the same subset, pairing of electrons, this is called pairing of electrons. 2 electrons in the same orbit, pairing of electrons, electron pair. So pairing of electrons in the same subcell does not take place until all the orbitals of the same subcell is occupied with single electrons. So all the orbitals will be occupied with single electrons, then pairing of the electrons will be occur, otherwise not. So this is going to be the Hund's rule. Okay, so why it is happening? Because electrons will try to avoid the inter-electronic repulsion, because when 2 electrons are present in the same orbital, there will be strong inter-electronic repulsion. That's why electrons will try to fill up with single electrons in all the orbitals, then pairing of electrons will be started. Otherwise, electrons will try, that means electrons always try to be unpaired. Okay, that means electron always try to maintain maximum number of spin. This is one spin, this is another spin, this is another spin. So electrons always try to maintain maximum number of spin. Okay, so this is called Hund's rule of maximum spin multiplicity. That means pairing of electrons will only occur if all the orbitals of the same subcell will be filled up with single electron. Then only pairing of electrons will be started. Clear? If I give you an example, like in case of boron, in case of boron, 2p1 orbital is there. Okay, so 2p1 is there, 1 electron in the 2p orbital. The rest 2 orbitals are vacant. In case of carbon, there are 2 electrons in the 2p orbitals in the last cell, so it is 2p2. Okay, so 2 electrons in the p orbitals. In case of nitrogen, 2p3, 3 electrons in the p orbital. Okay, 2p3, 3 electrons in the 2p orbital. So now you see all the electrons are filled up. All the electrons are filled up in the p orbital. Now for the next element, oxygen, which has 4 electrons in the 2p orbitals, in the last cell, in the configuration of oxygen, there are 4 electrons in the 2p orbitals. So in case of 4 electrons of the 2p orbital, first number 1 electron, number 2 electron and number 3 electrons will be placed in 3 orbitals, and then 4th electrons will be placed in the first p orbital, that means in px. Okay, that means the pairing of electrons occurs now in case of oxygen. Clear? So this is here it is maintaining the Hund's rule of maximum spin multiplicity. Okay. Now, how to express the electronic configuration of different atoms? So, how to express the electronic configuration, that means how many valence electrons are there in an atom. To express this, we have taken into consideration some core electrons, which are expressed in terms of inert gas atoms, and then only we express, after that we express the valence electrons that is shown in the following figure. Suppose in case of expression of these core electrons, we use the inert gas atoms. Okay. Helium contains 2 electrons. Helium, neon, argon, and krypton. These are the inert gas atoms, inert gas elements, right? Helium contains 2 electrons, so the configuration is, electronic configuration of helium is 1s2. The 2 electrons are present in the 1s orbital. Now, because 1s will be filled first, according to the pattern of energy of electron, 1s has the lowest energy, so 1s will be filled up first, so 1s2. Neon contains 10 electrons. So what is going to be the electronic configuration of neon? 1s2, then 2s2, then 2p6. There are 2 electrons in the 1s, then 2s will be filled up, so 2 electrons in the 2s, then 2p will be filled up, so 6 electrons in the 2p, because 2p means 2px, 2py, 2pz. Each room has the capacity to hold 2 electrons, so 2 plus 2 plus 2 total 2p6. So 1s2, 2s2, 2p6. This is going to be the electronic configuration of neon. So neon has 10 electrons. 2 plus 2 plus 6, total 10. Argon contains 18 electrons. 1s2, 2s2, 2p6, then 3s2, 3p6. After 2p, 3s orbital will be filled up, and then 3p. So 2 plus 2, 4 plus 6, 10 plus 2, 12 plus 6, 18 electrons in the valence shell of argon. So how to express? So these electrons are filled up in this way. Clear? Okay. Now here you can see that here I have shown you some elements where you can see the hydrogen, helium, lithium, beryllium, all the elements are there, and their corresponding atomic numbers are also there. So I have given the electronic configuration. Here you can see hydrogen. For hydrogen, 1s1, helium 1s2, lithium 3 electrons, so 1s2, 2s1. Beryllium 4 electrons, so 1s2, 2s2. Boron 5 electrons, 1s2, 2s2, 2p1. So in this way, all the electronic configuration are there. Now it's very boring to write. Suppose I am telling you write the electronic configuration of chlorine. There are 17 electrons. So you have to write all the things, 1s2, 2s2, 2p6, 3s2, 3p5. So it's better to write it in a shortcut way. How to express it? You always, if I tell you that write the electronic configuration of this element, then you go for the nearest noble gas atom. Suppose near 17, what is the nearest noble gas atom? Argon. But argon is higher than chlorine. The atomic number of argon is higher than chlorine. So you have to go for the nearest noble gas, that is neon. So you can express the electronic configuration of chlorine by expressing it as neon 3s2, 3p5. Up to 2p6 it is neon, Neon is 1s2, 2s2, 2p6. So chlorine electronic configuration you can write neon. Okay, you can write neon in the third bracket, then 3s2, 3p5. I want to let's elaborate this point. Suppose you have oxygen. So oxygen is 8, right? So if I go for the electronic configuration of oxygen, here you can see that oxygen has atomic number 8. So nearest oxygen noble gas or inert gas is helium. So helium we have to express it as helium. So helium is 2. So 1s2. So I am writing 1s2 configuration as helium, inert gas atom. 2s2, 2p4. So 4 plus 2, 6, and helium has atomic number 2. 6 plus 2, 8. If I go for the electronic configuration of aluminium, so nearest aluminium, the noble gas is neon. So neon has electronic configuration atomic number 10. So I can write the electronic configuration of aluminium as neon. Then after that 3s2, 3p1. Okay, because neon has the configuration 2s2, 2p6. Okay, so after 2p, 3s will come. So neon, it is the configuration of neon. It is the configuration of neon. So neon 3s2, 3p, neon 3s2, 3p1. So 2 plus 1, 3, 3 plus 10, Neon is 10, 3 plus 10, 13. Okay, 13 is the atomic number of aluminum. So in this way we have to write the electronic configuration of different elements. Clear? So in case of filling up of electrons that always occur from lower energy orbital, all the lower energy orbitals will be filled up, then higher energy orbitals will be filled up. So first lower energy orbitals will be filled up, then higher energy orbitals will be filled up according to this energy order of the orbitals. And this is given by Aufbau, the scientist Aufbau, and it is also called the Aufbau principle of filling up of electrons from lower energy orbitals to higher energy orbitals. Okay. Now we are coming to the last topic, that is called the exchange energy. So in the electron configuration or in the distribution of electrons in some orbitals, we have found some electron configurations that are exceptionally stabilized. Okay, such as p3 orbital, that means 3 electrons in the p subshell, p6 orbital, that means 6 electrons in the p subshell, d5 orbital, that means 5 electrons in the d subshell, or d10 orbital, that means 10 electrons in the d subshell. So all these electron configurations like p3, it could be any p3, 2p3, 3p3. So p3 orbital configuration, p6 configuration, d5 configuration, d10 configurations, all these configurations are very much stable. So what is the reason behind it? The reason is very simple, that electrons when present in some orbitals like d5, in the d orbitals or in the p orbitals, so if all the d orbitals are filled up with single electron, then it is called the half-filled set of orbital. Half-filled set of orbitals. All the orbitals are filled up by single electrons. So the entire set of electrons in this orbital is called the half-filled set of orbital. So in this half-filled set of orbitals, you can see over here that the electrons are present in the similar spin. All are upward spin. So all the electrons which are present in the upward spin can exchange their positions among themselves. That means the first electron can exchange their position with the second, first with third, first can exchange its position with the fourth or with the fifth, second can exchange its position with third, with the fourth. So any electrons can exchange its position with any electrons in the same subshell, since all these electrons are in the similar spin, So during this exchange of positions between the similar spin electrons, a vast amount of energy is released from this entire system. And when the vast amount of energy is released, the system attains a stability. Okay, and the energy released by these configurations like d5, d10, p3, p6 is called due to the exchange of electrons between the electrons of similar spin is called the exchange energy. So either half-filled set of orbitals, in the half-filled set of orbitals all the electrons can exchange their position and exchange energy is released, or in case of d10 configuration also, that means full-filled set of orbitals also, the electrons can exchange their positions accordingly. So now the confusion creates that which orbital, half-filled set of orbitals, that means d5 configuration, or full-filled set of orbitals, that means d10 configuration, which orbital will be very much stable. So d10 configuration, full-filled set of orbitals, where all the electrons are filled up, where each orbital contains 2 electrons, and it is d10 configuration. So in case of d10 configuration, the stability of the orbital is higher than d5 configuration, because in case of d10 configuration, the amount of exchange between the similar spin electrons will be more. Okay, so the vast amount of energy will be released as exchange energy, and the stability of the set of orbital d10 is much more than d5. Since although d5 configuration is also stable, but d10 configuration is more stable, because in case of d10 configuration, the 5 electrons in the upward spin will exchange their position, among themselves. Similarly, the 5 electrons present in the downward spin will exchange their positions among themselves. So a lot of exchange occurs between the positions of the electrons positions, and that's why a larger amount of energy will be released as exchange energy in case of full field shell configuration. So we can say that half field shell configuration and the full field shell configurations are very much stable. Why they are stable? This is because of exchange energy. Okay, so this is all about the important topics of structure of atom. Thank you.